马上后1968哎，
因为我觉得他写的很清楚，然后他证明很非常有。
那有时候就时过境迁，
是啊，
有些东西不需要写到这么清楚。
所以我就觉得
因为
很小的东西我知道而已。
哦，
啊，
但是你觉得他有解释到你那个啥
要
？OK，这样就好。
是到那里，
我没有看过哎，我要看一下。哪个不 action？做练习。
明白在干嘛？
要做一下练习哦，做一下练习。啊，可以看的，都可以，其实都可以。看人都可以。
看懂了啦，没有3个格子的时候，你也讲过270
想做练习的时候还是读的时候？这样你就去做练习咯。练习会告诉你什么地方你要注意看一下。那你做练习，反正你不要让自己停住就可以。停住你就会
如果我的那如果还有如果真的像他们这样。啊，这个是没病，这样咯。
好。
那个那这样。然后他讲的话，你可以读他的，你可以看到很清楚，就讲他没病。哎，因为一直猜讲我们看不到啊。Rebro 还有一个人他是自己是看不到。
等下再讲，等下再讲，可能他有一点 language 不太一样，等下再讲。Okay, there are a few things I want to say first before we start the lecture. So one thing is, have you seen your assignment 4 yet? No, which assignment already? 6. 6. Have you looked at assignment 6 yet? Look at it. Okay, so I want to give a hint on assignment 6. I want to give a hint on assignment 6. Let me find the hint. Okay. 哦，准备起来。Okay, so let's give some hint on assignment 6. Assignment 6. Question 3. Question 3, assignment 6. Question 3. On the question, suppose that G hat on X, then you want to show that the action. Okay, so you want to show that G mod N adding on X is faithful if only if kernel of phi is N. So what's this phi here? So N, let phi be the corresponding action of G. Okay. So I mean, you should ask a question. So this phi is an action of G, but why G mod N has an action? Okay. So the claim here is there's a natural action of this quotient map given the action of G. So what's this natural action here? So the claim is like this. So this is the claim. G, the action of G. So let me put the action. Action of. So the action G acting on X induce and action G mod N on X. Okay. So let me prove this claim here. Okay. So after I prove this claim, this is the definition you're going to use in your assignment. So first, this is a group action, we call it phi, right? So now we're going to define what is phi bar here. Okay, so we're going to define phi bar from G mod N cross S to S. Okay, so you need to define an action. Okay, so meaning you give me a Gn and an S. Okay, you need to tell me what is. We use the notation MGN, right? Okay, so what's this? Okay, what this is? Oh, yeah, what's this? Well, I mean, there are two ways to write this. Okay, so first way is to write like this. So Gn acting on X. Okay, how to define this? So how we define this is simply we just take G acting on X, okay, which is equals to phi of G phi of Gx like this. Okay. So we define this action of phi bar using phi. Okay, phi is given in the question. Okay. So how do you know how the coset add on S? I just look at how the representative add on X. Okay. Are you convinced that this is a group action or not? Is this a group action? So to prove that this is a group action, how many property you need to check? Two, right? Okay, identity law and associative law. Okay, so look at identity law first. So in this case, in G mod N, what's your identity here? Who is the identity coset? N, no? Okay, so you need to ask yourself whether phi bar N on S is equals to S or not. Is it equal to S? In this definition, is it equal to S? So what is phi bar N of X? By definition is, what's the representative for N? E, right? I can write it as, for example, phi bar E N X, right? So I pick E, E attain on X. But E is an element in where? In G. E is in G, S is X, right? So this is a group action that we use for phi here. But phi is a group action, meaning what? This is equal to identity. Okay, this is equal to S. Equals to S. Or if you like, you can go back to your group action first, and then this is equals to S because phi is a group action. Okay or not? So similarly, you want to check what? Associative law. Okay, you want to check associative law. So what do you need to do? You need to check that phi bar of G. What is associative? You do one by one, two together. So you do together is equals to you do one by one. How to do one by one? G1n on P bar G2n x. That correct? Do together, do at one go equals to do separately. Maybe you write a little bit different than what is right in the definition of group action, right? So in the group definition of group action, how I write it? So let me write at the side here. So if G acting on X, this implies that G1, G2 on S is equals to what? G2 on X first, and then G1 on X. Okay. But in this case here, I put these I call the composition as phi bar here. Okay. You understand or not? If you don't understand, look at here. Look at here. So I call this composition as phi bar. Okay, image of phi bar. Okay, so that's why I write like this. Because if you write this out, okay, we just write it out. So if you write it out, it's just G1, G2n composed on X is equals to G2n composed on X, and then G1n composed on X. Okay. Yeah. Okay. So I mean, why is this true? Why is this true? This is true also by the definition of our map here. How do we define this map? We just look at how the representative add on S. Okay, how the representative of X. On one side, what do you get? G2 on X, and then G1 on G2 on X. But the other side, but this side, how? Hey, what's wrong?被切掉，好看吗？为什么这样啊？OK，突然间把我字切掉了。OK， so on one side, how is this side? What to do this side? You need normal or not? Seems like you need normal. You need normal here to write like G1, G2n on X. You need normal. And then this is just G1, G2 dot X, and then equals to G1 on G2 on X. But this is what? This is the associativity coming from the phi itself. Seems like you need normal. Let me check. Did I use it? Oh, I didn't prove for them. Did I prove for them? Just prove well defined. Right. Need well, you need normal here. Yeah, you need normal. Okay, you need normal. Yeah. So that question actually work for normal n only. Question 3. Okay, so in question 3, this n is normal. So assume n is normal. Okay, question 3. Yeah, assume n is normal, only then you can show this associative law. Okay, otherwise how you multiply two coset together? You cannot multiply two coset together. So if you want to multiply two coset together, only works in normal. Only works with quotient by a normal subgroup. Okay, if not, you cannot multiply coset together. G mod n still makes sense. G mod any subgroup still makes sense. Why? Because the definition is it is a set of coset. So any subgroup you can remember cut your group, right? Okay. But only when n is normal, these coset can multiply together to form a group. Okay, otherwise they cannot. Because normal means what? Ng equals to Gn. Okay, so they commute with element. Okay or not? Other than that, actually you need to show that this map is well defined also. Okay, because again, you see when we do we need to check well defined map? Whenever you define your map using representative, you need to show well definedness. Okay, so let's say G1n equals to G2n. Why G1x equals to G2x? Sorry? Not quite. So how about number 0? So why I want to show well definedness of p bar. So why if G1n equals to G2n implies that G1x equals to G2x. Why? TFAE tells you what? By the last time, the TFAE theorem tells you what? G1, G2, which direction? Or G2, any direction is fine. G1, G2 inverse G1 is in is in N. Meaning what? In N means what? Meaning, yeah, meaning what? So meaning phi bar, let me think how to say this. Phi bar of G2 inverse G1 N is what? Yeah, so why? This is just G2 inverse. So, okay. So this one, okay. So let me put like this. So on one hand, okay. So let me write like this. So, okay. Okay, let me write this. On one hand, okay, on one hand, what do you get? You get G2 inverse G1 on X. On the other hand, what do you get? Phi bar of E on NX is equals to what? E on X, which is X. But not that what? G2 inverse G1N is equals to N, which is equals to E. And why? Because by the theorem we established, I mean, we use just now, we know that G2 inverse G1 is in N. Okay, so G2 inverse G1, yeah, G2 inverse G1 dot X equals to E dot X, which is X. What do you mean?
这个东西放的时候，你是没有秀它 well defined，你就已经说，因为它们两个的定义一样，就说它结论一样，你再用你要证的东西来做论证。
What do you mean? No, I mean their image is the same.
但是这个地方的 so 你不是已经在用你的结论在证明？
结论 is what?
对不对？
I know.
你在用你要证的。
I'm good in English, okay? I'm just asking you what's the conclusion you're pointing to.
你想要秀
啊？
这两个东西相等来推下面那两个相等，而且你就是在用你要证的东西在对呀，就是你的这个 so 不 make sense。你怎么来秀这两个相等，来通过秀这两个相等呢？这就是你要证的东西啊！你要证的就是这两个相等来推这两个相等。
No, I'm trying to show I'm assuming G1 n equals to G2 n. I want to show that G1 x equals to G2 x.
那
So
你怎么
what?
能用下面的那句话呢？你往下滑一点。
Yeah. What's wrong?
你这个 so 是怎么得出来的？这不 make sense。
So it's because they are coming from the same domain element.
但是你没有秀 well defined，你怎么能说它的 domain 一样就能推出它的函数值一样？
Oh, wait, let me think. No, wait, I mean, wait, let me think. Wait, let me think. 对，好吧，他看到有人要打架起来。What's wrong here? No, I want to prove this. I'm not trying to prove this. I'm not trying to prove this. This is my assumption. So I mean, okay. I think I did some extra work here. Actually, from here, right, I can already deduce G1 inverse G1 n is equal to n. That's all. No. I mean, I already know that these two are the same thing. Okay, so they should map to the same thing.
但是这个前提是你不要 define， 还是在用
对呀。
那个
Seems like right. Let me think.
表示的东西来走一个。
Yeah, let me think. What's wrong with it? I mean,
make the point 就是从最后去最后的那个 so 已经在用了，它是我要 define 的。
Let me think. Wait, let me think first. But the reason is not because the reason is not because it is well defined they are equal. The reason they are equal is because, let me think. The reason they are now you should show well definers here because it's not well defined.
为什么 n 里面的东西一定就都得送到同一个 s？ 为什么 n 里面的东西你作用在 s 上面就一定要送到 s？
By this definition here, because you look at n here. Okay, so let's look at n. Okay, look at n first. So what's the representative of n? You can just pick the identity en. Okay, so I mean, sure. And then by those definition, those should sense to identity also, because one of the representative is E. So E pretty much decide what all the other n have to do.
这个前提不就是这个函数是我要 define 的？
No, this is definition. So you need to understand what is definition and equality. Yeah. So after we define, then we check well defined. If you haven't defined, how to check? Nothing to check. So that's why I need to show to you it is well defined. So this is the job. So we are thinking now. Can you be patient a bit? Don't be purely bang. Okay. Be patient. Okay. Be patient. Patient is a key. Okay. Patient is key. Patient is key. Okay? Patient. Sure. Let me think first. Let me think. What's your problem? Because I don't understand your problem now yet. I think now I don't think I got any mistake yet. Let me think. Let me see.
你让我分解我的问题吗？
你可以吗？你可以吗？
我的问题就是在说你在定义的时候，就像你刚刚说的，我是在用那个 representative 来做定义。但是你这样子的话 ，n 里面它有很多个东西，不是 e， 没有办法确定 n 里面的其他东西作用在 s 上面。
Maybe you can speak English, otherwise they cannot listen.
I'm trying to say that there are another elements in S, and if you put that after that element on S, you cannot sure that it is just S.
I mean, this is just by definition. For example, we define a unfaithful representation. I mean, unfaithful action, right? What do? We just let every element act as an identity. That's all. It's the same thing here. So if I gonna define this, how this concept act on X, right? I just look at one representative. That's all.
那我问一下，如果比如说我 n 里面有一个 a， 这样子的话 ，a n 也会送到 a 乘 s， 对不对
？Well, okay, you need to be careful here. You need to be careful here. Here we are looking at concept element. It's not look at small n.
我知道，但是 if there is a
Okay. I mean, okay. So. Yeah.
重点是在你已经选好了，你进去了，你才证明各位要define，它是两个没有选。
对 ，so we need to pick first.
对
，so we need to pick first.
它的 representative 已经定了每个，它已经定了每个 concept representative 是不会变的。但是像你说的，要是一个 concept 里面有很多 representative， 那肯定不会要 define 啊。因为同一个 concept 里面你可以拿很多种 representative。
I think I get what you mean.
所以为什么
I think I get what you mean. I think I get what you mean. I think I get what you
他
mean.
已经选好了每个 concept 就定那个东西了。
是我已经选好那个东西。
Yeah, I think you are right. Yeah, I think you are right.
我懂他的意思，但是
Yeah, I think he is right. I think he is right. So I mean, we can do anything. We can define any action. I think you are okay. I think Adrian point out a very good point. So I mean, for example, like okay, I know what the problem now. Okay, can sit down. Thank you. Okay, I know what's the problem now. Okay, good. Okay, good. So here, okay. So I mean, his problem was which representative we need to pick, right? So potentially, right, if you pick different representative, then that concept will act differently based on my phi. Okay, but for example, in this case, n, the representative I'm gonna pick is en. Actually, we only need to specify this because we only need to check for identity law, which is very important. The other one you can pick differently, like for other gn you can pick differently. But for n, this one I think we have to be specific. We need to pick en as the representative so that this n concept will act as a act trivially. Okay, so that this n concept will act trivially. Like if you're gonna pick different n, right? So maybe you pick another n1 out of this n, right? So potentially, n1 add on x might not be equals to e add on x. Potentially, depend on phi. Right or not? Yeah, depend on phi. But for the special n here, we're gonna pick en. Yeah, for others, it's okay. Never mind. Just for n here, we need to pick. Yeah. Okay, so that's why this well-definers reduce to the case to G inverse G1 n equals to n. So in this case here, you can see that G2 inverse G1 x equals to x. And then you can use the argument that we discussed in class, right? It's not cancellation law, but this will imply that G1 x equals to G2 x. Show for general concept. 哪里不能这么写？
因为你不一定推出来的是 GDS 等于 G8。
Because
按照你的定义，不管它们都是到了同一个极端，比如
So wait. So first line here is by definition, right? Second line here is also by our choice. So second line here is by choice actually, by construction. Okay, no. This one by construction, no? Because we pick n to be en. And then the top one is by definition.
第一行不应该等于第二负一次方 GS， 不然它不是要被发生的。
没有。So I mean， 没有问题，我觉得没有问题。This is definition. So this line is by definition.
是如果说，比如说
No, because we already know that these two cosets is the same.
these two cosets is the same, but you
So it's just n.
yes, but you cannot say that.
No, it's equals to ex, right?
就我觉得你这个地方在用的定义已经是我刚刚在说的东西了，不是 A 刚刚说的东西。
你听得出来讲什么？
就 G2有没有 G2不一定和 G1 cancel 的呀，不一定是 E，所以它可能是其他 element， 然后你
然后你刚刚说
你 add on
其
S
他
的时候，它不一定是 S 而已。
对啊。So this one implies that G1 dot x equals to x, right? So this one implies this line was wrong.
那个 G2 G1 你没有，你又不能定着说它这样可以是等于 E 啊。
听不懂。我 I mean, do you know how I get this line or not? Do you know how I get this line? 哪一个？这个说 because they are coming from the same thing. This is n. This is the n that we know already.
这个式子，这个等号就不一定能成立啊，因为按你的定义方式是 choose 了那个 n 就是 en 嘛，那你这个地方你送到的就是 es， 不可能是其他的东西。对，它不一定是 E 啊。
你写 G2 有没有 G 乘 S 等于 S 你就有问题哦。
哪里？
就是你这个等号，你把它等成 G2 负一次方 GS 的时候就已经有问题了，因为按照你刚刚给我解释的，你的定义方式是我只把 n 送到了 ES， 所以你这个地方不能再
没有 ，sorry， 再来一次 ，sorry 啊，我这边 actually I really send GN to GX, but for n the special n I send it to EX. That's all.
那如果是
General GN I still send it to GX, but for n the special n we send it to EX.
那如果我 n 里面比如说有个 A， 那我 AN 会 send 到 AS， 你怎么确保 AS？
Wait, so say again.
就那个他已经定了，他直接打1罢了。
对啊，那他已经定了，下面就不能再那么写了呀。
这样就更快了，如果你要的话。什么意思？听不懂。
哦。
什么意思？讲看。
你把一个 n 送到 ES， 就是其他的东西你根本不应该把它送到 G2 负一次方 GE。
啊？什么？再
他讲你选好，已经选好 E 啊，然后你会说嘞，这个 G2 inverse G 又是在那个 n 里面，然后你又拿一个新的对不出来啊？
对啊。
问题。
然后你怎么确保？那就像我刚刚问的问题，如果我 n 里面有一个 A， 那我 AN 会等于 n， 你怎么保证 AS 一定等于 S？
讲慢一点。
好，如果我 n 里面有一个 ，if there is an A in n, then AN equals to n. How do you make sure that AS equals to S?
就是你
Okay, so wait
不一定是 n。
you so you mean you take an A in n, and then you look at AN, right? Okay.
Then phi bar AN equals to AS by definition. And the phi bar n equals to S by definition. How do you make sure that AS equals to S?
Okay, because okay, so I think for n1 we need to define separately. So for all the n, we need to see it as so an. So since A is in n, AN is equals to n. So the representative we pick for this special n is En. Okay, so AS have to act like ES. You get what I mean?
所以这样你就得加前提的，也就是
Yeah， 所以我现在加。
OK
Yeah， 我加。Yes。
你加这个前提我就 make sense 了。
Okay, makes sense. Okay, thank you.
哦，它是
Hey, if it makes sense, you also have to make sense, because we spend a lot of time here. Yeah, if not, you have to ask question.
你是拿那个橘的地毯，
Yeah.
它是一个前摇滑，不是
Yeah, 我不是 Yeah, I mean, so we know that n, whatever n, have to go to EX. For any a in n, an have to go to EX. Okay, this one is we fixed one. For general G not in n, we send it to GX. So now we want to show well-definers for general Gn. Yeah, that's all. So meaning well-definers, okay, like what he said, well-definers for n, you cannot show one. Then what is by definition or by construction? And you need to send everything in n. So you need to send every representative in n that let it add trivially. Okay, yeah. That well-definers you cannot show. That's why it's by definition, by construction. And then from there, you can deduce that for any general 2 coset, they should add the same, regardless what representative you pick. Okay or not? 有问题吗？我去消化一下有问题要问的。Okay, yeah. Supposingly, this part you need to write in your. Supposedly, you need to write this part in your assignment. Okay. 你是最近做了主席是吗？听说。哇，所以你要带我们去到哪一个高度呢？Oh, we also got a vice president here. Raisa. Okay. Yeah. Okay. What time now? 7:30. If you can write, you can try and write this part fully inside your assignment. But I think I won't grade it. Okay, but yeah, because I tell you answer already. So if you like, you can practice in your assignment. If not, you can just use the map here. Okay, you just use that map. You just use the quotient action. Okay, quotient group action. Okay, so you can either use it or you can try and prove it, but I won't mark it because I will produce this proof for you. Okay, so you can just use it. Understand? 有问题吗？ I think this part is harder than you prove the faithfulness thing. Yeah, this part is more technical. Faithfulness is just play around with the kernel. Okay. Yeah, the hard part here is sometimes you need to treat n as an element, or sometimes you treat n as a set. Okay, so this is the thing that you need to go between. Actually, I wanted to share another thing about free group. You want to know about free group or you want to go to ring first? Free group. Okay, let's talk some extra thing on free group. Because I think some of you keep constantly confused with this notation here. Okay, sometimes you are quite worrying about this E here. So E here, I mean, when we talk about free group, right, we define it as an equivalent class actually. Okay, so what does it mean, equivalent class here? So for example here, what are the empty set here? I mean empty word. So these are all the Okay, now I want to tell you some conceptual thinking about this free group. Yeah, some conceptual, but quite precise. Okay, let me ask you, what are the equivalence empty word inside this group presentation here? X squared, right? Y cube, right? And then yx, and then their product. Okay or no? Their product. And then so on. You can produce a lot. Right or not? Even conjugate of these words, right? So xy cube, x inverse. A bit careful here. A bit careful, because now we want to talk about relation here, right? So we need to talk about the word that evaluate to identity. So I think it's a better way to write this one as yx. Okay, and then here I conjugate like this. Okay, so these are the equivalent classes. Is it? 对还是不对啊？我知道很多。Is conjugation here or not? Let me ask you a question. Here? Conjugation here or not? I think maybe not. Just product of them. We think. Is conjugation inside there? We think. It is in there, right? Okay, so let's think about this context here. Let's think about this context. So what map you look at? This one. This is in assignment which one? Assignment 5, right? Okay. So you look at a map into where? Into S3, right? So S3, you know the exact elements here. So identity 1, 2, 2, 3, and then 1, 3, and then 1, 2, 3, and then 1, 3, 2. Okay. So you can pick a map, right? You can pick up a map. So for example, let's pick X to 1, 2, and then Y to, for example, 1, 2, 3. Okay. I mean, you can pick differently, right? But this is one of the choices. But what is the thing that evaluate to identity? So what's the thing that evaluate to identity here? So let's make this a different color. So to represent, this is element wise. Okay. So, well, I mean, you should be able to put conjugation, right? So like x, y, cube, x inverse here, for example. Okay, so how should you think about this x thingy? Actually, this is how we record, I mean, how you do calculation here. For example, what is identity here? You can do 1, 2, 1, 2 here. So the other side that represent this 1, 2, 1, 2 is x squared. Okay, and then what else you can do here? You also can do yx is what? Maybe do 1, 2, 3 cube. Okay, so 1, 2, 3 cube represented by what? Y cube. So meaning what? When you draw this free group, or this group presentation here, this word is what your calculation did, what you did in your calculation, in your real life calculation. Okay, actually, free group or group presentation will record, okay, all kind of calculation that you did in S3. Okay or not? You understand? You understand 吗？明白我讲什么吗？就是说这些 free group 这些字这些 word 我们叫做 word 嘛，这些 word 其实是在记录所有你计算的可能性。如果你算的话，你看这个就是1，看这个又是1， but 这些其实就长得不一样，对不对？一个是12乘12嘛，一个是123乘3次嘛。Then we record it as S and Y。我记住它的那个1是怎么来。Understand? So in free group we try to record or every calculation. Okay, every calculation that you can do in your group. Okay or not? Does it make sense? So that's why we say they are isomorphic. Why? 如果你讲，哎呀，反正它都是记一样东西，怎么不要等于就好了？怎么不要等于？不要等于？就 isomorphic 吧，怎么不要等于 ？Why not just equal？两边都是 set 嘛，对不对？怎么不要等于就好了？算一样东西，怎么不要等于？ When we say set equality means what? The element has to be the same. But on one side, the element 是什么 ？X 跟 Y 做出来的。On the other side 呢 is cycle。cycle 跟 XY 不是明显不一样的东西。You understand? Okay, so that's why we only can talk about isomorphism here. So isomorphism here says what? As long as you have a map, the map is projective and homomorphism. Yeah. Okay. 什么？晶晶，看谁要看谁，不知道要 change。
S3等于 presentation。
哦，OK。So this one, yeah. So 要再 check 一下，你看，so 这个是一个重点。So if you read my definition, there's a very important point here. You look at my definition, You look at my definition. 差一点被骗了，是不是 ？Okay. The group has a presentation. We'll put equal here. By right is isomorphic. You see, if G is isomorphic, by right is isomorphic. But why I put equal here? Yeah, you should think about it. Okay. So in this case here, yeah. So this group is general. So let me see if I write anything here now. Okay, I think I didn't make any. Here I put here. Why we write G equals to the presentation instead of just isomorphic? Okay, by right it's just isomorphic. But why I put equal? Because we want to emphasize that it is really only the relation that governing the composition in the group. Only relation matters actually. Or not. I can have, for example, just now S3 you prove that it is a free group of 2 order with 3 relation, right? So maybe you have a free group with 2 order 2, but with different relation. Then with different relation, then your group changed already. But still generate by 2 elements only. Okay, so really only the relation matters here. Okay, it's not the function composition. It's not how you send the n indexes. Okay, it's not matrix multiplication. It's not addition. Okay, it's just asking you if you put 2 things together, it equals to what? That's all. Okay, this is about group presentation. I only need to know when I put these 2 things together, what is it equal to? Or put 3 things together, or few things together, what is it equal to? That's all. I don't need to do composition one. I don't need to do function composition. I don't need to do addition. I don't need to do subtraction or anything else. You just tell me if I put these things together, what it equals to. That's all. Is it enough? Okay. Correct or not? In S3, in the exam, right, you need to compute how to compose together. But here just tells you what? You just need to remember 3 relations. Okay? You can compute everything already. Okay or not? Okay? Yeah. So that's why we abstract the calculation, okay, into relation only. No need to go into actual computation. Can you speak louder in English? Can you speak louder in English?
And then how do you find all the relation in?
So given a group, how to find relation? This is a very hard question. Super hard. It's very hard. In general, it's very hard, this question. In general, this question is very hard. Yeah. Maybe generator is still easy to do. You just just show that every element can generate by these few generators. But relation is hard. How hard is it? It is as if you want to show something is injective. So if you know that identity gets sent to identity, how do you know that the rest of the element gets sent to whether they get sent to identity or not? I don't know. If you don't check everyone, how do you know? Okay, so this is a very important question in the frontier of mathematics. So we prove faithfulness of group action, for example. We want to know whether the kernel that corresponds to this group action is equals to identity element or not. Is faithful or not. Whether this kernel is only consists of identity or not. It's very hard. In general, it's very hard. Okay, give you a group, create a relation, it's very hard. Maybe you can create some, but how do you know you get enough? This is a very important question. Very hard. In general, it's very hard. Yeah, in general, it's very hard. So that's why the problem that we gave you is very specific one. For example, look at S3, look at those are known. Those isomorphisms are known. In general, it's very hard. Okay. Okay or no? Any other question? Any other question? Actually, there are some part on this free group action. There are some remark that I didn't go through in class, but you have to read. Because if I mention this remark in the class, I don't think you will get it and you won't appreciate it also. But after you do assignment, after you think about it, go back and read. I think you will learn more. You will know what I'm talking about. Okay, yeah. Or if I have time, or then I can comment. If no, please read. Okay, whatever I put in my notes, you please read. Okay, and the typeset one, the typeset one is also updated to the latest version, so you can read also. If you found any typo or anything you are not sure, you should contact me or contact Eric. Okay, Shu Yao also on or Ziming also can. Ziming, right? Yeah, Shu Yao or Ziming. Okay. No question or not? Before we take a break. No? I acknowledge this group action and group presentation free group is the hardest again in this course. After that, we go to ring theory. Almost is repeating what we did in group. So we will learn group, we will learn ring, sub-ring, product ring, quotient ring. And then we will learn a new thing, it's called ideal. This ideal will replace the role of normal subgroup in group. Okay. So meaning what? Quotient ring is a ring quotient by an ideal. Okay. Ideal, you know Chinese is what? 我理想啊，我还以为是美好。Okay, let's take a break until X03. Okay, let's take a break until X03. 理想型。太旧了这本书，1968我还没有生，而且他们没有用这本书。Yeah. 说就是这种哦，没有，我不会生气，我不会生气。OK， 对，
看你刚刚也挺激动的。
我是这样的，
真的就是理想。
是，我知道，但是我一直会把它想成美好。
这个美好有什么？
之后我也是觉得差不多。
有
理想美好，
别吧。
理想比较高。
美好
不一定是理想。
理想啊。
那理想可能在
理想怎么不美？怎么才能不美？
理想
哦，理想，
我觉得他们描绘的东西不太一样。
是高的。
我知道他要讲什么哎，有些东西很理想，但是它不一定很美好。
比如，这好像什么？
哦，
别在我眼里是不理想。
哎，
我不是讲你们，我是讲
general
哎，我想到
什么
补充个小问题，那个 conjugate 在里面是因为它是 normal generate，
啊？我知道，
所以会在哪？
我后来想到，
我知道，
问题是为什么我们要考虑 normal，也是因为它过去的时候它会 cancel。
差不多，其实差不多。
但是如果它不 normal，它可能
比较
不一定，I mean 不是，就是 normal 的东西被送过去也是一，所以你一定要
加
把它，你一定要把它切掉，不然的话它切不掉。
对，不然根本没法切。
对啊，没法切啊，就不能说代表对面可以被 cancel 的情况。
哎，我问一下他们英语系的一个问题 ，caution 可以当动词用吗？
他们是数学系可以。
什么 caution？
或者说英语的人
我要 caution。
可以当动词用吗？
对啊，为什么？
可以，
可以？
可以吗？
那有 caution。
因为他的 lecture notes 里面写了一个 caution， 我就在想这玩意儿人家 ing。
caution 挺
你要讲 caution 吧？
在 caution 白吗？
我觉得这个词不能加 ing。
不然
没有啊，我没有看过，没有。
百就是已经是
caution 摆就可以，caution
No no no，it
是什么？
it's caution
他
by
caution 加
something。
了 ing。
可能你要 dash ing 哦，dash ing。
要的，
开干以后了，开干以后。
有一个 ing 不可以放，
我知道，
定
可以把它变成数学里面的动词。
你那个开那个好像那个黄色那个讲很多，
他说不要打听让我听我
开那个讲很多那个，
可以不？
开那个还他超你久那个。
哦，
我以为是
啊，这个，没有看一下吧。开那个这里应该不用，这里应该不可以写。
什么？
开那个这里应该不可以写。
什么？
应该不可以写 s 出来。
我觉得不可以，但是如果他说要讨论，如果他用这个讨论的话，如果他是要用
没有啊，现在重点就是好不想用这个讨论啊，我们要规避这种，我们要规避。
对，对，
所以其实应该不可以写 s， 因为只有你在这个题目上面你才可以放 gs。
对，其实你一定要这样看，这样看的。
就分两个 case 啊，这样。
对，要分两个 case，对。
A in n 的话 ，an since 是等于
呀，因为
或者
刚才还要再讲这个东西。
是啊，
是啊，我会
不可以写 as 啊？
呀，我会擦掉这个，就是刚才在讨论 AS 的时候，其实要把它 define 成 EX。
是吧？因为你are not using this rule even。because you're not even using this rule 嘛 ，because 你要规避。
或者你要的话也可以，或者你要就这样 for all AN， 这个也包这个 EN 进去了嘛。
呀，是。
所以意思说，你 define 这 map 的时候是要看它 representative 到底躲在 N 里面还是没有躲在 N 里面。
那其实就是因为你要符合 identity rule， 所以你要 define 那个东西对，还是 like 它其实是 trivial 还是白了，对吧？
对，就是要把 N 里面全部东西 map 成 identity 吧。这样的话才会自然的 induce 一个 map on portion。
一定要的是吗？
因为你把这里 N 的东西看成 identity element 嘛，这样的话它应该要 act like identity 嘛。
Yeah, true, but that's no reason。你一定要 construct， 一定要 construct 这样啊。
必须要求这样才能。
Yeah, true. I know. If I will do like this, that works, but like
你讲为什么一定要这样啊？
也不讲一定要这样，我知道为什么一定要这样，但是就是为什么要写出来，就是为什么也不讲为什么要写出来，但是就是
为什么要看这个？
有点怎讲哦，就是为什么要？
你觉得你在想问为什么要定义这么一个 map？
不，这个当然懂了，这个不懂也无所谓嘛，他定义了嘛，但重点是在于
为什么它是自然的？
为什么是自然？白天的。
不是，
自然，我觉得很自然。
没有嘛，自然自不自然不是重点啊，重点是在于
真的就是它自然，它有点两样。
他这样做的话，他就把 N 看成。
对。
对，他 supposed to be 这样子。
对啊。
其实背后的核心原因就在因为 an 是等于 n 是吗？
啊。
对啊。
所
以你就是被迫要让他的 es 啊。
他被迫全部 represent。
他被迫去变 es 嘛？全要变 es 啊，对啊。 是啊，
因为你
它不 ignite
因为你要用
不，
你要用旧的那个东西的时候，你一定要讲回它的 element，
是啊是啊
所以你从 cosine 里面找 element 出来，一定是找它的 representative。
嗯，
对啊，但是所以它的 representative 必须 act 来，
对啊，
没法这么做。
要不要教我这种？
可以，等一下，我要点名一下，
不用，你点名看的是啊，
要点，
没有喊的是点名吧，喊这样。
我不认识的，我不太知道他在哪里，我就要点，知道他在哪里我就关心。
看一下
给我翻译一下。
，interesting，
什么？
好的呢，
我要听，
听什么东西？
听你要跟他讲的。
哦，等一下，因为他那个是 extra 的，所以还没教。
哦，你发现
那你今天教到差不多教完了，早上还看。哎，这个是4，应该是看
6，你在讲6啊？
看6是下个礼拜，5是教了，
这是5，
所以还没教。
明天，
有我微信
有人有 assistant，但是我看
你干嘛要问他一个？
又是那几个？
对呀，
可是多少几个就有点危险。
想哦。
有没有几个？
我说你刚刚为什么要问他？你以为我加过我
2、3个。
哦，
你本来看到
有些没有来问。
红杰也有呢，红杰。
那本书，那书比较难。
指明。
哦，我看
指明 you say when you extend until your assignment. This fifth of 2 days after. Okay. 你这个子涵呢？子涵，it's 子涵 here， 子涵，真子涵。OK。林金，
我也觉得他是中国人。
金鱼，have you submitted your assignment? Haven't finished 啊？好。Tomorrow.
0。
OK。
你刚刚问 when 而不是 how 吗？
啊，
我说你刚刚不是应该问 when 而不是 how 吗？
我比较只想知道 how，我不想知道 when。
其实他回答的是 when 不是 how。
他只回答了 when 也回答了 how，回答了 when 不一定回答了 how，怎么办？
哦，
啊，how 知道 how 他通常回答就是我会2天后交这样。那也是啊，但是他们就会觉得是好，tomorrow 这样子。
哦，对，
是把他们觉得 how 就是tomorrow。
喂，
带一层呢？带一层
你没来 how 还是 how come 还是
啊？tonight 啊，OK。
how 就是怎样？你要怎样？所以你这样打嘛，所以就根本没有错的。所以其实根本是。
冰下，
他来了。
来了，
做李浩在后面，他们现在
这个是
朋友的朋友。
OK。
人脉认高。啊，对，哪个店哪个香？啊，哪个店哪个香？啊，哎，不错，姓啥？不知道，无所谓。
参与，你找到 turn it in 了吗？你找到那个查窗了吗？找到了，交了。一凡呢？一凡有这样。哦，厕所 OK。好，
厕所就是 A， 厕所就是 A。这几个人啊？
啊
52个，
好多人哦，好多人。
有啊。
好多不是好。
Ian, how's your assignment? Tomorrow. OK。
别逼他了，我感觉他。
对，你怎么知道？
他说我们有一些进步圈里的朋友跟我说，是他死掉了。
他死掉，
他就有点想休学了。
Year one, sem 3 还是 year 2 sem 1，一般要小心。
金鹏，
开玩笑的。
哎，金鹏，你前几次为什么没来？闪到腰啊，爬不起来啊，
都这样狠吗你？
走路辛苦，坐着很辛苦。
做什么？
反正也到来。哎，
其他
啊！我说他其他科也缺的不是针对你。
我知道，我是问到。
我刚第二刚才说什么，然后我现在忘了。
Okay, let's continue. Okay, let's continue with rings. Okay, so let's recall what ring is. So let's make a comparison between groups and rings. Okay, so what's groups and what's ring? First of all, obviously they are the set. Okay, so they are set. So meaning there are elements there. Okay. In groups, what do you have? You have a L or C. Okay, you have a L or C. So LC from where to where? G cross G to G. In group, what else do you need? You need a identity. You also need a inverses for all elements. Enough? Enough or not for group? Oh, good, very good point. Associative. Yeah, very good. Associativity. Okay, associative law, associative LOC. Very good. I think that's all. So, but in ring, what do you have? Instead of one LOC, you have two. You have two LOC here. Okay, in two LOC here, you call it what? Class and multiplication. Okay, so under multiplication, under addition, R is an abelian group. So meaning what? You have all the group property for your addition. Moreover, it is commutative. Okay, you can commute x plus y equals to y plus x. But under multiplication, what do you have? It is commutative. Also has associative. Okay, associative. And also has an identity. No inverse. No inverse. If you have multiplicative inverse, later we'll define it as a field. Okay, it's a field. And then since you have addition and multiplication, right? So how these two put together? Okay, in high school, you will say open a bracket, right? Open bracket. So what's open bracket? You need to use distributivity. You distribute addition over multiplication, or you distribute multiplication over addition. Okay. Okay. Continue. So we'll define subring. So what's subring? So it's like a subgroup. So subring, you should expect what? It is a subset. Okay. So what property have to satisfy? It's a subset. Yeah, good, very good. A very important point. It has to be closed. Closed under what? So here, closed under addition, subtraction, and multiplication. Okay, that's all. And it contains the multiplicative identity. Okay, so maybe you ask a question. Inverse is a problem. How about zero? Is zero inside there or not? Is zero inside there? Why? Why zero inside there? Addition, right? But how do you add until you get zero? So where's the negative here? Subtraction. Okay, so if like me, I don't like subtraction, right? I only like addition and multiplication, right? So if you remove the word subtraction, then your definition need to add 0 yourself, and then you need to add in all the additive inverses. Okay, so subtraction here take care of additive. Okay, let me write here. So this one would imply all the additive inverses and also the additive identity 0, because if you have a x, you can take x plus minus x here to get 0 because it's close. Okay, yeah. If you don't like subtraction, then you need to add these two things in, 0 and additive inverses. Okay. Or in other words, a subring is just a subset of ring that satisfy all the ring axiom. Like what we prove for subgroup. Okay, the subset that satisfy all the group axiom. But in ring, subring is not nice. Later I will show you, maybe I'll show you why subring is not nice. Nicer thing is ideal. Okay. So let's give example first before we talk about these things. So I'll give examples. So what sort of ring you have seen before? Z, okay? Start from number. Z, R, right? And so before R, you have rational number, right? Complex, good. Complex number, yeah. Natural number, got or not? You need to add in the 0 inside. Got or not? No, right? Why no? Good. So there's no additive inverse for some of the element. For all the non-zero. So no additive inverse for non-zero element. Okay. Also, we have ZP, right? Finite element here. So we can multiply. Or in general, there's something called the Gauss integer. Okay, so Gauss integer is like a complex number, a discrete version of complex number. So it's called Zi. So what's Zi here? Meaning the coefficient I just take from Z. Can you imagine this or not? So complex number you can imagine as a complex plane, right? Okay, complex plane, so X and IY. But if you just take A plus BI means what? You take a lattice of it. Okay, the Z lattice. Okay, okay. Okay, you take the Z lattice. Can you see the Z lattice or not? Like if you take 1, 2, 3, right? On x-axis, also 1, 2, 3 on y-axis. Okay, so these are where all your Gauss integer live in. Okay, the lattice. Okay, right. For example, this point here is 2 plus I. Right or not? Yeah. Maybe I make a different color so that more visible a bit. What else? What else form a rings? For example, continuous function from R to R. Hey, actually, I realized that this notation was taught in your linear algebra, is it? Right or not? In your linear algebra notes, you have this kind of notation, right? CR. So this is a continuous function from R to R. How to add continuous function? How to add continuous function? So if I give you two function here, fg. Sorry? 什么叫直接接啊? So it has to be a function, right? So you need to tell me what is f plus g on x. Is what? fx plus gs, this is what we call by addition pointwise. Sorry, 我在这。哦 sorry. 难怪我 G 不见掉，原来被他偷掉。Okay, so this is what we call addition pointwise. Okay, pointwise addition. Actually, pointwise addition is the lousiest addition. Yeah, because this is the most primitive one. For example, multiplication. Also, you can multiply pointwise. Okay, also you can multiply pointwise. Okay. What's not ring? For example, what's not ring? So I claim that the matrix n by n matrix is not a ring. Why? Why is it not a ring? Determining 没有 inverse， 零是没有 inverse， 没有 inverse is what? Multiplicative inverse, right? But ring doesn't require multiplicative inverse. Not commute, right? Mn doesn't commute because the ring we consider is commutative ring. Okay, it's not a ring. Okay, because the ring that we consider is commutative ring. Ring we consider are commutative. Okay, so when I say this, a ring is commutative, don't ask me, 老师，你讲 ring 是 commutative， 它加法 commutative 还是乘法 commutative？ 不要问这样的问题好不好？为什么不要问这样的问题？ Because addition always commutative. It's an abelian group. So any adjective we add on rings is for multiplication. Okay? Yeah. So remember, if I say the ring doesn't have multiplicative identity, what's the ring called? You know? If you don't have ring, if you don't have multiplicative identity here, what's the ring called? You can call it ring. Rank. Yeah, rank. There's no I there. Rank. No identity. 真的，书有这样写，书有这样写，我不是开玩笑，我没有开玩笑，没有，他真的 define rank. Yeah. Also, you can, if you go to Wikipedia, you could have group which is don't have identity one or don't have inverses one. Okay, so they are different things. One is monoid, one is magma, something. Yeah. Magma. Huh? What do you mean? 少掉就不是 group 了嘛，对不对？没有讲 group， 就少掉它是其他名词，对不起。Okay. But this is a perfectly good non-commutative ring. Okay, and then there's a topic that's studying non-commutative ring. Yeah, but why we study commutative ring? Because we don't need to do things twice. Okay, if you study non-commutative, then multiply from the left, multiply from the right is different. So you need to do things twice. But here, no need. So there are non-commutative geometry also, yeah, which is also a field in interest. Lastly, not yet, still got many. So number 4 is called a polynomial ring. Okay, so this is a very important ring in this topic here. In this topic, because we will explore the property of a polynomial ring here. So note that I put this R here. This is 我不是写错啊，这个 R 不是 real number 的 R. This R means a general ring. So we build a ring on top of a ring. We use ring to build ring. Okay or not? So in this case here, n by n here, I can replace with general R also. So meaning what? Meaning I can put these things in inside my matrix or inside my matrix. I can put Z, I can put Q, I can put R, I can put C, I can put ZP. Or I also can put function. Also can. A matrix of function got this kind of thing. Matrix of function. Okay. Okay, so what's polynomial ring here? So polynomial ring is really easy to define. So how do we define here? So this notation, you keep seeing until the end of week 15, which is, we call it R adjoint X. R square bracket X. So we'll call it R adjoint X. Later, we'll define it again. R square bracket. Okay, R square bracket X. We call it R adjoint X. Adjoint. ADJOIN. Okay. So what's this here? So this is really easy. So what is this? This is just a finite sum of monomial with coefficient. Where does this coefficient live in? This coefficient live in the ring R. Okay. So it's a finite sum here. You can stop one. Okay. Now, for example, what is the example here? You can see. So for example, let's say 1 plus x, or 1 plus a1x. Like that. Okay. But it's finite, it's finite. Okay, so this is the main player we're gonna play later. I want to do some extra thing out of here. Maybe it will help with your analysis. Maybe don't, but just bear with me first. So the next one I want to introduce is called a formal power series. What's power series to you? Infinite sum, right? Okay, so here we'll put double square bracket here. Okay, where this coefficient will live in the ring also. And then this power will go to infinity. Maybe you will ask a question. Whenever you see an infinite sum, infinite or sequence, you should ask a question. Yes, this converges or not. Okay, that's why you learn a lot of tests. Alternating series tests. Cannot recall. 全部还给陶先了。Ratio tests, yeah, good. Okay, but here we don't care actually. Okay, in this class we don't care. We don't care about convergence. We just write out this form. That's why we call a formal power series. It's just some variables put together. Okay, we don't care about convergence. In algebra, we don't care. Okay, we just care it as an object, formal object. Okay, it's a formal object. We don't apply it as a function. Okay, we don't care. Next is a rational polynomial over a ring. Yes, over a ring. So how do we define this? This one we will put R bracket S. Hey, is it clear that how we add these together? Okay, let me ask you a question. Is it clear that how we add two finite sum together? You just add coefficient by coefficient with the same power of x. 懂我在讲吗? So let me quickly write down, because I think you need it for your assignment. So if you're gonna add two potentially different sum together, what do you do? You just depend on m greater or equal to m, right? So you just add up. Let's say let's say if m greater than n, you just add up to m, and then you add out the corresponding coefficient together, and then multiply. Just distribute. Okay, no, just distribute. Yeah, if you multiply two finite sum together. Okay, so similarly, you can apply to this infinite series. It's the same. It's the same. Okay. So what is a rational polynomial here? So it's P over Q such that P and Q live in the polynomial ring of X. So meaning you are dividing, taking quotient of finite sum here. Okay, such that they don't have common factor. You see, the description here is really similar to the definition of rational numbers. Okay, rational numbers. So later we'll do something similar to polynomial ring. Okay. Have no. Okay. Okay, so here is a square round bracket. So this is the difference. So round bracket we can do division. Okay, what else? Lorentz polynomial. Have you heard of Lorentz polynomial before? Lorentz polynomial. 认识 Lorentz 这个人吗？不认识哈。Okay, so Lorentz, because finite, because polynomial ring, you just extend on one end, right? Positive end. Or for power series, you just extend in a positive power. Lorentz polynomial here can extend two ways. Okay, so let's say adjoint with x and x inverse. So you have a finite sum ranging from negative power to positive power. Okay, so let me give you one examples here. So what sort of examples here? For examples, x plus, sorry, do the other way. X inverse plus x. This kind of polynomial exists. Because in polynomial ring, you just have positive power. Former power series also positive power. But now we include negative power. Okay. So what's the next thing we can do? Here is finite, right? We can consider infinite. Okay, so that one we will call a Lorentz series. So infinite is series. So we can consider Lorentz series. Okay, then you will cover everything already, I think. So can you guess the notation here? You want to guess the notation? So if I have a polynomial ring, okay, if I extend it to infinite, I put double square. But now Lorentz, 啊，还是两个？两个什么？啊，两个反括号。Okay, surprisingly, it's like this. Double round bracket of x. Hey, so there's a reason here. Maybe you think that it's not consistent, but there's a relation between rational polynomial and this guy. Okay, yeah. So you should think that this double bracket is coming from this single bracket here. Okay, so there's a relation actually between these two. So actually the inverses of one finite sum can look something like this. I mean, think about it. I mean, yeah. We won't play around with these things, but I want you to think about it. So my claim is here. So there is a relation. The relation between rational polynomial with Lorentz series. Okay. Try go and find it. But we won't play around with these things. Okay. Okay, let's continue play with a ring. Ring is kind of fun to play. A proposition. A ring. Let's say we require 1 and 0 to appear inside our ring, right? What if 1 equals 0? Can you imagine what happened? Let's say the additive identity is equal to the multiplicative identity. What will happen? What? 加跟减肯定不一样，但是addition and multiplication is different, but these two elements is the same. So meaning what? So meaning, let's say let's do some proof sketch here. So let's say 0 plus anything in R is R, right? But 1 acts like R. And because 1 is a multiplicative identity, right? But if 1 and 0 is the same, then 0 also act like 1. So what will happen here? What will happen? 天下大乱. What will happen? Huh? Right? 1 equals 0. Yeah, 1 equals 0. Yeah. So assumption is 1 equals 0. So what happened to this ring? what will happen? Do you recognize that R times 0 is 0? You know how to prove this? I think your MA didn't did this proof. But this is a very elementary proof you need to know. So 0 times R, why is it 0? Because 0 times R is 0 plus 0. But times is distributive, so you get 0 dot R plus 0 dot R. So by cancellation law, you will get 0 dot R equals to 0. Okay, so this is how you 为什么老师告诉你零乘全部东西就是零就是了，零乘全部东西就是零，零乘全部东西就是零。Why? Because 0 is the additive entity here. 可以想得出吗 ？What happened to our ring if I tell you this hint here? 对，那个东西是什么？就是零。Why 啊？ So if you look at all, OK， 猜是很好，但是因为你现在是数学系啊，你要证明你的猜想。OK， so if you take every element in your R, what is R? R can be written as 1 times R, but 1 is equals to 0. 0 times R is 0. So everything is 0. So meaning a ring such that element 1 and 0 is the same is a what we call a 0 ring. Okay, inside that only 0. 0 times 0, 0 plus 0, everything is 0. It works, it's a ring, perfectly good ring. It's like a trivial group. Inside a trivial group only have identity. Okay. So this ring is not nice. It's just a trivial ring. Okay. So next, we're gonna define what is called a unique. Okay, sorry, unique, not unique, unique. But it's unique. Okay, so unique. So what's a unique of a ring? Okay, a unit is a ring of a ring is an element that is invertible, or we call that it has a multiplicative inverse. Okay, so just now the question says that whether a ring have a multiplicative inverse or not it is equivalent to ask whether this ring has a unique or not. Or has a unique. For example, what is the unique in Z? What sort of unique you have in Z? 1? 还有吗？还有 unit 吗？ What else is invertible in Z? 2 invertible 吗？ 二分之一 half is not in there, right? So 2 is not a unit. What else? Negative 1, good. That's all. Okay, 1 and negative 1 because they are on multiplicative inverse. How about Zi? Let's say I consider all the A plus B items. What's the unit inside here? Do you remember this set or not? A plus bi such that A and B is in Z. What are the unit here? Actually, there's some hidden thing I didn't tell you. I have to satisfy I squared equals to -1. Okay, I hope you know that. But we need to write it explicitly if this is done properly. So, what? Plus minus 1 still in there, right? It's unique also, right? What else? Anything else? Plus minus I, good, very good. That's all, 4 of them. Okay, so this is the root of unity, the 4th root of unity. Okay, or the 4th root of unity. How about the polynomial ring? Okay, finite sum of polynomial in X. What are the unit here? Who are invertible? Who has a multiplicative inverse? Constant. 0 include or not? No, right? Okay, so all the non-zero X, non-zero R. Okay, yeah. Okay, so I mean, you can try and figure out what are the uniques in all the ring that I gave you just now. And then we'll go to the definition of a field finally. So what's a field? So a field is a ring such that it is not a zero ring. Okay, so meaning 1 is not equal to 0. And every, okay, and it's every non-zero element is invertible. So which means non-zero element is a unique. Okay, so can you give me an example of field or not? Huh? Rational number. Okay, what else? Real numbers. Good. Okay. Complex. Good. Anything else? Okay, so the Rx I defined just now, which is called the rational polynomial. Okay, it's a field. You can prove it. Find the inverses. And also the Lorentz series. Okay, so that's why I put square bracket, round bracket here. Usually when we put round bracket, we will mean that it will form a field. Square bracket is just a ring. Any field you want to talk about? Any other field that you want to talk about? You mean like this? Is it invertible? So you say that what is this? This is equals to square root 2 times square root 2 over 2. Sure. Think makes sense. Does it make sense or not? If you combination, sorry, A plus B, right? This one. So this one, the inverse, 这个也有。Okay, 来。Mean conjugate So is this conjugating word or not? It works, right? And square plus 2b minus okay, minus. Okay. Good. Inverse is the same. I mean, this inverse. Oh, right. Okay, to be precise, this inverse is the multiplicative inverse here. So meaning if you take a plus b square root 2, multiply with a minus b square root 2 over a square minus 2b square, you should get 1. But it's clear that you get 1, right? Because how you get this denominator, you really just by multiply the 2 conjugate together. Hey, by the way, I use conjugation here. This conjugation is not the GG inverse conjugate. It's different. So conjugation in complex number is different than the conjugation in group elements. It's really different. I think I gave an example inside lecture notes. It's different. Okay, so be careful. Unfortunately, there's a terminology crisis here. We use same word for different things. Okay. Yeah. So far, what you learn in linear algebra is field. I mean the scalar you use is field. Okay. God bless you. So let's start with a polynomial ring now. Okay, so the moral here, okay, I want to remind you. So the moral here is polynomial ring is like integer. Okay, please remember this line. Slogan here, Rx is like integer. Okay, so whenever we introduce a property for polynomial ring, you should think about whether Z has this property or not. Okay, so think about it. Okay, Remember already? Please remember, whenever you think about polynomial rings, please think about integer. Later, I will show you how similar they are. All right, so let's do it properly here. So let's define. What does it call as a polynomial ring with coefficient in R? Okay, what is it? It is a finite linear combination. Okay, so a combination of what? Of powers of the variable x. Okay, so quite straightforward here. So how do you write it out in general? So let's write out fx equals to an fx to the n plus an minus 1 x to the power n minus 1 and then so on. Okay, such that these AIs are the elements in R. And more importantly, these monomials, you shouldn't think of it as a function. I'm not trying to substitute x to be real number, complex or anything. It's just some we call it an intermediate. Okay. Or we just call it a variable. So I think this is the first word you heard about it. Or sometimes we just call it a placeholder. Okay. You know, you are not trying to evaluate this polynomial, nothing like that. You don't see it as a function. Okay, you see it as a formal polynomial here. Okay or not? Okay, because for example, in your calculus class, right, whenever you see like fx equals to x squared, right, your brain is like connected to this graph, right? Okay, this is when you want to evaluate this function here. So what is f1, what is f2, like that. But we are not trying to do all these things. Okay, if you want to do this, please enroll in algebraic geometry next time. Okay. So we are not going to do this here. Okay, yeah. Right, so we just plainly understand the polynomial. Okay. So if you collect all these polynomials together, this is what we call the R square bracket x or R adjoint x. And so if you consider all polynomials with coefficients in a ring R, this is what we call the ring Rx. Okay, no? Okay, please remember. So the element inside this ring is polynomials over R. So far, okay. Nothing special yet. For example, how many things you can put here? So here you can put random R here. Let's give an example here. So what sort of ring you can, what sort of coefficient you can consider? Maybe integers, okay, or complex, or real, or Gauss integer, or ZPX, or maybe you want to put a n times n at the side. Okay, let's give some example for you to imagine. So for example, in Zx, you could have 1 plus x. In Cx, you could have Ix, for example, correct? Ix. Coefficient in I. Real number, maybe square root 2 times x. And then this one is pretty similar, maybe something like this. I think ZP is a kind of boring. So let's do this one. Maybe we can put what to put here. Let's say 2 by 2 matrix. So when n equals to 2, what happened? Maybe I can put something like this. Yeah, it's possible. Okay, maybe put 1, 1, 1, 1, x 100 also can. Yeah, possible. Coefficient could be anything. In fact, in real life, this happens more. Do you think of why? In real life, this kind of thing happens more. Why in real life, matrix is more favor than these numbers? Do you know why? In real life? Yes, data. Because when you take data, right, there are a lot of variables. And then usually these variables are, if you cannot find relation, then they are linearly independent with each other. But the more complicated one was, maybe they have some correlation between these variables. Yeah. That one is more complicated, actually. Linearly independent is still easier, because you have basis. But if they are not linearly independent, then you need to build relation between the elements or the vector. Okay? Okay, so next, what's the next thing? Every time we define an object, I need to tell you when two objects is the same. Okay, when are they the same? So when are two polynomials equals, what do you think? When is two polynomials equal? What do you think? If all their coefficients are equal. Okay, so based on the coefficient only is enough. Just decide based on coefficient. So mathematically speaking, what do you need to do? So if you have f, okay, you have f, and then you also have g. How do you compare them? Well, let's say we have gx such that b0, b1x goes up to bn xm. When are they the same? Fx equals gx, if and only if all the ai equals to bi. Okay, for all. Okay or not? Okay, so you just really need to see the coefficient is now. So the coefficient here is very important. And well, we need to introduce another thing here. What is linearly dependent means? Okay, or independent means. So let S be a subring of R. Then we'll say that R1 up to Rn in R are linearly independent over independent over X means what? Want to guess or not? Refresh your linear algebra memory. Is linearly independent means what? If you can write a linear combination of R1 up to Rn equals to 0, then x1 equals to x2 equals to x3. Okay, so this equation, the first equation here is what we call a linear dependence relation. Anyone not know what this condition trying to say? You know why this condition set like this? Okay, so let's say for example, let's say x1 is 1, x2 is 2, then you will get x1, and then the rest was 0. Okay, so how do I put this? So sj equals 0, for all j greater than equal to greater than 2. Yeah, thank you. Then you have R1 equals to 2 times R2. This means what? This means that if you multiply R2 by a coefficient in your, let's say in this case S, then you will get R1. Then you will get R1. So meaning what? Actually, I can forget R1. How do I get R1? Multiply 2 on R2. Okay, no. Why is it linear? Why is it linear? Because R2 is just power 1. No. I didn't look at R1 square. I didn't look at R1 cube, R2 cube. No. It's just single power. So linear? No. Linear graph is what? Y equals to mx plus c. Because x is single power. If it's x squared, what do you call? Y equals to mx squared. Quadratic. Yes, good. Potentially, you can consider like quadratic dependent relation. Also got one. Quadratic dependent. But in our case, we just look at linear. Linear independent. Okay. Yeah, so remark here. So we want to remark here. So you should show that the monomials are really linearly independent. Correct or not? X and x squared should be linearly independent. Can you multiply any scalar to get x squared or not from x? You shouldn't. Okay, you cannot. Because x is a placeholder or intermediate. Hey, the time is out. I haven't finished define everything yet. Maybe we can stop here. So maybe we'll stop here. We will continue on the Thursday. Okay, there's a lot of definition we need to define, and we can do things. Okay, see you on Thursday. 哪里啊？没有，我是讲这个是一个这个东西是一个 linearly dependent relation。等于零这两句加起来，一等了过后才 linearly independent。对。
你这句话是干嘛？为什么前面写这个？
通常我们的 scalar 是活在 ring 里面。通常我们的 scalar 活在 ring 里面。比如说 Rx 的 coefficient 是在 R 吗 ？R 其实就是 Rx 里面的一个 subring。
再说一遍。
coefficient， 比如说 polynomial ring over R， 那个 R 本身是 Rx 的 subring， 所以你可以任意选。
所以其实就是这个 S1、S2、S 是要属于 S 的。
对，
不然我觉得你应该写，要不然你这句话不是很浪费，写在这边很。
sorry 啊，漏了 ，sorry。
你想说的是这些东西要属于 S 的。
对。
OK，
不然我 over X 没有意义。